When you first set eyes on the Burj Khalifa, it's hard not to feel a sense of awe. This incredible structure pierces the sky, reaching a staggering height of 828 meters, or 2,717 feet. It's not just tall, it's the tallest building in the world, and it's right here in Dubai, rising from the desert sands like a modern-day miracle. But hang on a minute, desert sands? That's right, this mammoth structure, along with Dubai's other skyscrapers, is built on what was once nothing but shifting desert. The Burj Khalifa isn't just a feat of height, it's a triumph of engineering ingenuity. It stands as a testament to human ability to overcome seemingly impossible challenges. Now, let's talk about sand. Not just any sand, mind you, but desert sand. Desert sand presents a unique and formidable challenge to engineers. The problem with desert sand is its shape. Unlike beach sand, desert sand is relatively young. Its grains are rounder and smoother. These smooth grains don't lock together well. They're more like tiny ball bearings, constantly shifting. This makes it a nightmare for construction. Yet, Dubai's skyline continues to grow taller. How? That's where human ingenuity comes in. Here's a fact that might blow your mind. Dubai, a city surrounded by desert, actually imports sand for construction. Yes, you read that right. It's one of those paradoxes that make engineering so fascinating. But why on earth would a desert city need to import sand? The answer lies in the quality of the sand. As we discussed earlier, desert sand is too fine and smooth for construction. It simply doesn't have the right properties to make strong concrete or provide a stable foundation. So, Dubai imports coarser sand from other countries, often from as far away as Australia. This imported sand has angular grains that lock together much more effectively. When mixed into concrete, it creates a stronger, more durable material. Using local desert sand would require enormous amounts of energy to process it into a usable form. In many cases, it's actually more environmentally friendly to import suitable sand from elsewhere. Now let's dig deep, literally. One of the key techniques used to keep Dubai's skyscrapers standing tall is the use of deep piles. These are essentially giant underground pillars that anchor the building to more stable layers of earth beneath the desert sand. In the case of the Burj Khalifa, these piles are mind-bogglingly deep. They extend 50 meters, or 164 feet, underground. These piles are made of reinforced concrete and are designed to distribute the enormous weight of the skyscraper over a wider area. The arrangement of these piles is crucial too. They're laid out in a specific pattern, often resembling a wagon wheel when viewed from above. This design helps to spread the load evenly and prevent any one area from bearing too much weight. The process of installing these piles is a feat of engineering in itself. Massive drilling rigs bore deep into the earth, often working around the clock. As they drill, they pump a special slurry into the hole to prevent it from collapsing. Once the desired depth is reached, a cage of reinforced steel is lowered into the hole, and then it's filled with concrete. Section 5. Foundation design, the key to stability. The foundation of a skyscraper is like the roots of a tree, invisible but crucial. In Dubai, foundation design becomes an art form. The Burj Khalifa's foundation is deep and wide. It sits on a massive concrete raft 3.7 meters thick. This raft spreads over 8,500 square meters. This wide base distributes the building's weight. The foundation is designed to be flexible. Flexibility allows swaying in high winds or seismic activity. High-tech gadgets monitor shifts or movements. This ensures stability and safety in challenging conditions. Section 6. Flexibility in the face of wind. When you look at a skyscraper, flexible probably isn't the first word that comes to mind. But believe it or not, flexibility is a crucial feature of these towering structures, especially when it comes to dealing with wind. First, it's important to understand that all tall buildings move. It's not something you'd notice from the ground, but at the top of a skyscraper, this movement can be quite significant. The Burj Khalifa, for instance, is designed to sway by up to 1.5 meters, or 5 feet at its top. This swaying ability is built into the very structure of the building. The Burj Khalifa uses a unique buttressed core design, where the central core is supported by 3 wings that extend outwards. This design allows the building to confuse the wind, breaking up the airflow and reducing the forces on the structure. The building's exterior is also designed with wind in mind. The cladding panels are specially shaped to minimize wind resistance. As the building rises, it gradually changes shape, becoming more slender towards the top. Section 7. Concrete innovations pumping to new heights. Now let's talk about concrete. It might not sound exciting, but when you're building the world's tallest structure, even something as basic as concrete becomes a fascinating engineering challenge. The Burj Khalifa required some serious concrete innovation to reach its dizzying height. One of the biggest challenges was simply getting the concrete to where it needed to be. Pumping concrete up to such extreme heights had never been done before. The previous record for concrete pumping was about 470 meters, or 1,542 feet, but the Burj Khalifa needed to go much higher. To solve this problem, engineers developed a special high-strength concrete mix. This mix included special additives that kept it liquid for longer, giving workers more time to pour and shape it before it started to set. The pumping system itself was a marvel of engineering. Powerful pumps at ground level forced the concrete up through a network of pipes. The concrete was pumped in stages with intermediate holding tanks along the way. Section 8. The role of technology in construction. In the world of modern skyscraper construction, technology plays a starring role. From computer simulations to GPS-guided cranes, cutting-edge tech is what makes these architectural marvels possible. One of the most important technological tools is computer modeling. Before a single brick is laid, engineers create detailed three-dimensional models of the entire building. These models allow them to simulate how the structure will respond to various forces, from wind to earthquakes. They can test different designs and materials virtually, identifying potential problems before they become real-world issues. GPS technology is another game changer. In a building as tall as the Burj Khalifa, even tiny errors in alignment can become major problems hundreds of meters up. To ensure perfect vertical alignment, construction teams use GPS-guided cranes and laser-guided surveying equipment. This technology allows for precision down to the millimeter, even at extreme heights. Modern skyscrapers are equipped with a network of sensors that constantly monitor the building's health. Section 9. Future innovations rotating skyscrapers. Now let's take a peek into the future. As impressive as Dubai's current skyscrapers are, the city isn't content to rest on its laurels. Plans are already in the works for the next generation of architectural marvels, including a concept that sounds like it's straight out of a sci-fi movie: rotating skyscrapers. The idea behind a rotating skyscraper is both simple and mind-boggling. Imagine a building where each floor can rotate independently of the others. The result would be a constantly changing skyline, with the building's shape morphing throughout the day. This design could have practical benefits too, like allowing residents to follow the sun or avoid strong winds. One proposed design for a rotating skyscraper in Dubai is the dynamic tower. In this concept, each floor would be prefabricated and then attached to a central core. The floors would be able to rotate 360 degrees, powered by wind turbines hidden between each floor. Section 10. Environmental considerations in desert architecture. Building skyscrapers in a desert environment isn't just about overcoming structural challenges. It's also about creating buildings that can withstand and even thrive in extreme heat. One of the biggest challenges is cooling. In a city where summer temperatures can soar above 40 degrees Celsius, keeping a skyscraper cool is no small feat. The Burj Khalifa, for example, uses a sophisticated cooling system that collects and reuses condensation from air conditioning units. This reclaimed water is used for irrigation and to supply the building's cooling system, saving millions of gallons of water each year. The building's exterior also plays a crucial role in temperature control. The Burj Khalifa is clad in specially designed glass panels that reflect heat while still allowing natural light to enter. This helps to reduce the load on the air conditioning system, saving energy and keeping the interior comfortable. Dubai's skyscrapers are also incorporating green spaces into their designs. Section 11. Conclusion. Human ingenuity, reaching for the sky. As we've explored the engineering marvels that keep Dubai's skyscrapers standing tall, one thing becomes clear. These structures are far more than just tall buildings. They're testaments to human ingenuity, creativity, and our relentless drive to push the boundaries of what's possible. From the deep piles anchoring them to the earth, to the flexible designs allowing them to sway in the wind, Every aspect of these skyscrapers has been carefully engineered to overcome the unique challenges of building in a desert environment. The solutions are as diverse as they are innovative, importing sand from across the globe, pumping concrete to unprecedented heights, and using cutting-edge technology to monitor and maintain these structures. But perhaps what's most impressive is the forward-thinking nature of Dubai's architectural ambitions. As we look to the future with concepts like rotating skyscrapers, it's clear that the city's skyline will continue to evolve and amaze. In the shifting sands of the desert, humanity has built mountains of glass and steel, reaching ever higher into the sky.